Hello, this is Dr. Stutzman, and today we're going to talk about differential equations. So, differential equation connects differentials, which are rates of change, to values of a function. And it happens a lot, people study it in a lot of places. It could be a scientist, it could be a physical scientist, like chemist, an engineer, a biologist, or a physicist, or it could be a social scientist, like a economist. A differential equation relates measurements and the rates of change. So here's some examples of some differential equations. Um, First one has dy dx equals um, x times y. The second one has a second derivative. The third one has a third derivative and some second derivatives. And these are, and sometimes there's functions on the left and the right. Notice that the first one only has the first derivative of y, so it's a first order. Second one has a second derivative. Third one has a third derivative. So the order of a differential equation is just the highest derivative that shows up, the highest order derivative. And if you want to find a solution, and there's going to be a lot of them that we don't know how to solve in this course this year, but you have something that's called a solution of a differential equation. If you take y equals f of x and its derivatives, plug it into the equation, it comes out to be true. So our first one was dy dx is x times y. And this is kind of abstract, but I'm not going to tell you how we can find the answer. But if I told you that f of x, y f of x is e to the 1/2 x squared, then what is dy dx? Well, that's going to be the derivative of e to the 1/2 x squared, which is using the chain rule. It'll be e to the 1/2 x squared times the derivative of the inside, which is 1/2 x squared times 1/2 times 2x, or just x, which is x e to the 1/2 x squared, which is x times y. So we found a solution. Didn't know how we found the solution, but we found a solution because if I take my solution, which is y equals e to the 1/2 x squared, take its derivatives and plug it into the original equation, it comes out to be true. Well, we're going to solve differential equations, a special kind of differential equation tomorrow and for next video. But today we're going to use our first order differential equations to approximate a function. So in Euler's method, we're given dy dx, which can be calculated given current values of x and y. We're going to approximate y at a nearby value using successive linear approximations. So let's remind what a linear approximation is. Just a simple one. We did this when we first learned about derivatives. Here is a curve, and there is the derivative at a point, which looks a lot like the function. If we zoom in, looks a lot like the function in a very close range around x. And I'm going to use it to approximate a new value, which is a little bit farther away. Now, it's going to be off, but it'd be somewhat close depending how close we are. So I'm going to zoom in, give it an initial value x0, which gives me a point x0, y0. I want to approximate a new point at x1, which using the line will be x1, y1. How do you get that approximation? Well, slope is dy dx, dy over dx, or approximately the change in y over the change of x, which we calculate by subtracting the new y value minus the old value y value. If I move some things around, I move the x1, the delta x to the other side, I get y1 minus y0 is my change in y, is m times the change in x, or y1 is y0 plus m delta x. So the new value of y is equal to the old value of y plus the change in y, which we can get by calculating using the slope times how much x changes. Well, Euler's method is going to do this repeatedly. Instead of just doing one step, we're going to do multiple steps to approximate the function. So we're going to always be calculating a new the new value of y is the old value of y plus the slope times the step size. The step size is the change in x values. And I might tell you how much I want to make a step each time. It could be some number like 0.1 or 1 or something. Or I can calculate it by knowing what I want my final value of x to be minus my initial value of steps, new value of my old value of x divided by how many steps I have. So here's an example. dy dx is equal to 2x minus y. I can easily calculate the slope at any point by taking 2 times the x value minus the y value. And I'm going to start at the point 2, 3. So you can kind of see on my graph that I'm starting at the point 2, 3. That's my x0. Now, what you notice with all these little lines in here is kind of showing what the slope is using this calculation for every point. So if I calculate for the point dy dx, for when x equals 2 and y equals 3, my slope is equal to 2 times the x value minus the y value, or 2 times 2 minus 3, which is 4 minus 3, which is 1. So when x equals 2 and y equals 3, the slope should be 1, which kind of looks like what that slope is. If I plug in a different point, let's say the point 1 for x and 2 for y, the slope should come out to be 2 times 1 minus 2, which is 0. And we notice that when x equals 1 and y equals 2, the slope is 0. Or if I put in a point x equals 0 and y equals 3, the slope should be 2 times 0 minus 3, which is negative 3, or negative 3 slope, which we kind of see right here. And this is doing this, these little red lines are showing the slope at any point. All right, so let's approximate y of 1.4 starting out at y equals 2. So I'm going to calculate my step size. I start out at 2. I want to end up at 1.4 using 3 steps, which means that x is going to be equal, the step size is going to be equal to negative 0.2. I want to go back 0.2 each time. So step is 0.2. And my initial point, x0, is 2. My first point is, my first y value is 3. And it'd be helpful using Euler's method to go through some steps. So here is step number, step 0. We start out at x equals 0. X equals 2 and y equals 3. Calculate the slope, which is dy dx, which is, in this case, 2x minus y. So my slope's going to be 2 times 2 minus 3, which is 1. And so my change in y will be my slope times my change in x, which we know my change in x was negative 0.2 because that's the step size. Slope is 1. So my change in y will be 1 times negative 0.2, or negative 0.2. Which means that the next step, when y equals, next step, my x is going to go down by 0.2. So it's going to be 2 minus 0.2, or 1.8. My y will be 3 minus 0.2, or 2.8. My slope is now calculated differently. It's going to be, well, it's calculated the same way, but using different numbers. 2 times 1.8 minus 2.8, which comes out to be a slope of 0.8. And so my change in y will be 0.8 times negative 0.2, or negative 0.16. So at the next step, my x goes down by another 0.2. My y goes down by 0.16, or to 2.64. My slope is now going to be 2 times 1.6 minus 2.64, which is 0.56. So my next y value will be 0.56. The next change in y times 0.2 or minus 0.112. So my last step, I end up at 1.4. My y value would be 2.53-ish. And I can stop because I ended up at my final point. So my approximate y 1.4 is approximately equal to 2.53. All right, let's take a look at how that happened. So here's our initial point, and there are my slopes at all these points. And I'm going to draw a tangent line using my slope, which was 1 at that point. I'm going to go a step of 0.2 away to the left to give me a new x value. Notice this here, the slope is a little bit more shallow. And my next step is going to be to x equals 0.6, 1.6, which can be the next x value. I get a new tangent line at that point. And there is my final point at y equals 1.4 and x equals 1.4 and y equals 2.53. Now, the actual solution to this differential equation, y equals 2x minus y, dy dx equals 2x minus y, is equal to this curve, which is e squared e to the negative x plus 2x minus 2, which this is beyond the scope of this class, how we got that solution. But that gives you this curve. And notice that our value of x3, of y3 is a little bit off, but it's better than if I would have taken the line, the first red line, and gone down and just made a jump all the way to 1.4 for my linear approximation. Just by doing simple line calculations, I get to a value of 2.53, where the real value is about 2.6-ish. So not bad. All right, let's do one more example. dy dx equal to x squared divided by y squared. And we start out at y equals 0. We're going to approximate y equals 0.3, and we'll make a step of 0.1 each time. So I'm going to be methodical, make a chart that keeps track of my current value of x, my current value of y, how much my slope is going to be, which in this case calculated to be x squared divided by y squared. And then I get my change in y, which would be my slope times my step size, which in this case is 0.1. So I start out at x equals 0, y equals 1. My slope is 0 over 1, which is 0. So my new y is going to be my slope is 0 times my step size, which is 0.1, which is 0, which means I'm not going to change my y value, which seems like, well, I'm doing nothing. But let's see what happens when I make my next step. The next step, x is going to go up by my step, which is 0.1. My y is not changed because it went up by 0. But my new slope would be 0.1 squared divided by 1, or 0.01. So now my y is going to change. It'll be 0.01 times my step size, which is 0.1, or 0.001, which means my new y will be 1 plus 0.001, or 1.001. X goes up to be not 0.02, but 0.2. My slope is 0.2 squared divided by 1.01, 1.001, which is not exactly, but really close to 0.04. 0.04, a little bit less than 0.04. Delta y is going to be my 0.04 times 0.1 or 0.004. So my final y value will be add 0.04 to it, or 0.005, 1.005. So y when x equals 0.3 is approximately equal to 1.005 using 3 steps for 0.1. All right, here's one for you to do. This is an AP question from 2021. You can go to you can search for AP from 2021, the B, C. You can see them work out the problem. This is has lots of problems, lots of pieces to this one problem. Part B is using Euler's method, using start at x equals 1, where we know that the first y value is 4, approximate when x equals 2, using 2 steps, which means calculate how big should my step be if I go 2 steps starting at 1 and ending up at 2. And you should get an answer of 4 plus 3 times the natural log of 1.5 using this. It's also worth practicing your Taylor polynomials, which is the first part of the problem. And tomorrow we'll talk about particular solutions, how to solve the differential equation. And that'll be tomorrow, which will be to find an answer like this. All right, I'll see you on the next video.